Okay, this is the spider and fly problem. We'll start off with the fly one. There's a funny side effect that happens when we do this one. So if I'm going to label these corners A, B, C, D, I actually want to know the length AC. Now there is a weird effect that you can actually go straight to AD. I'll talk about that as we go through. So by Pythagoras, AC squared is the hypotenuse, because it's the right angle there, is equal to AB squared plus BC squared. And that means that AC squared is equal to, we had 6 along the AB side, plus BC, which is 4. 36 plus 16 is 52. So AC is the square root of 52. Now, this is where the weird thing happens. To get AD, what I have to do is I have to do AC squared, which is actually this 52. Well, AC squared from the first line is actually A squared plus AB squared plus BC squared. They both give us this value. And I need to add to it the height, CD. So in terms of algebra, we've got our distance going along the back, AB squared plus BC squared, gives me that part, plus CD squared. Then following that, from there, it actually means that if I want to know the length in 3 dimensions between 2 points, I do the length in one direction, then a length right angles to it, and then a length right angles to that. Effectively, we can do length of a line in 3 dimensions is the length, the distances in x, y, and z directions, 3 different directions, all added together. That's Pythagoras in 3D. Okay, so I can now come through and solve my problem. The AD is the 52, actually let's do it using the full formula. So it's 6 AD squared is 6 squared plus 4 squared plus 2 squared. So it's 56, and AD is the square root of 56. If I pull in my calculator, we've got square root, let's do the 6 squared, plus 4 squared, plus 2 squared. Square root of that answer, and I've got 7.48 meters. The reason I've gone to 2 places is that's the distance in centimeters. Okay, so the fly, corner to corner, does 7.8 meters. And we did that by AD squared equals 6 squared plus 4 squared plus 2 squared. And that gives us AD, the diagonal distance across. That's the first one. So now we're going to consider the spider. Now there was a tip given on this one that the spider, just scroll it at the bottom, might be sensible to consider the net of the cuboid. So let's do a net of a cuboid. If I can get this screen to position nicely. There we go. So a cuboid, we have a base, and I'm going to use 1 square for 1 unit. So I'm going to draw the net. I think, can I do it full size? I might be able to do it full size actually. Yeah, that's 4, 3, 6. So the bottom, there's A, there's B, there's C, and then D is when I fold this out 2. So this point here is D on top. So this is the vertical height 2 going up that edge. Rest of the net, let's draw them in. Just make sure we've got everything we can. And this point here is D as well. Now this is where it gets a little bit weird, is we've got a choice of 2 lines if we're going to just run through. Hopefully you've all realised that both of these, if you're going diagonally across the top and then straight down, you're not efficiently spreading out how you move vertically. So these two actually are not the best solution. We're looking for some solution like that one. And there's 2 ways of doing it. You've got cutting across the short side and cutting across a longer side. Which length is better? Now, eventually you might actually be able to do it by reasoning. My reasoning on it would be, if I was to make this taller and taller and taller, what would happen is, cutting through the short side, you're getting closer and closer and closer to just adding the 2 lengths together. But as this gets taller, we've still got a significant diagonal happening. That's taking limits is the idea. So I need to label the 2 positions. So let's label that one D1 and D2. They are the same point, but they've got 2 in a different direction. Okay. So let's consider the first method, which is cutting along the short side. Short side, we've got a right angled triangle. The distance AD1 is AB plus the distance B to the top. So we need to know this length here as well, which is the same as that. So this is 6, 2, and 4. So my side now, A to this position X. So AX squared D D1 squared. So X D1 squared. Put the numbers in. AX is 8. It's the sum of the 2 sides. And XD is 4. Go through normal Pythagoras. AD1 is the square root of 36 plus 16, which is 52. Square root of 52 64. 18 is not 52, it's 82. 64. 16, sorry, it's 80. Well, let's use the calculator to do it. 8 squared plus 4 squared should be 80. Square root it, and we get 8.94, or 8.9, yeah, 94 meters. Let's try the different route, the AD2. Now some people think these are the same, they're not. So we want to go from A to B, and then B to D2. So what are those lengths? Well, AB is 6 squared, BD is 4 plus 2, which is another 6 squared. That gives me 72. So AD2 is the square root of 72. So 6 squared plus 6 squared. Notice we're adding these lengths before we square, and square root the answer. And that gives me 8.49. So we've actually got 2 possible solutions here, and the best one is this 849, which cuts along the long side. So going corner to corner in this position, the fly has the advantage that it can save a metre in flight. So that's fine for it as long as its speed is more than 1/7.5 the speed of the spider. As long as the spider is actually doing faster, or 7.48 over 8.49 the speed, then it will always get to the corner first.